people started to say, okay, if it cannot, maybe diffusion is not the right thing to do. Well, not everybody going to buy this word, so a bunch of people started to work on it. And what they did, they said, like, one thing that we learned from the diffusion process is that we can make a Markov chain, right? So diffusion process in physics, for us, is a Markov chain, right? So we have a Markov chain starting from data, and this Markov chain, every time it's going to pass this data through one process, it's going to give us one thing, right? And that thing is supposedly noisier version of the data, right? And then again, we get that one, we add noise, we add noise, we add noise, till we get to the noise, right? So this is the Markov chain process. So we have the forward one. The question is that, do we have the backward one? So is there a Markov chain which looks at the last sample, and then it just generates the next sample, which is distributed exactly like xt here is distributed exactly like this one? Does it exist? And you can do a tiny bit of math to show that actually it can exist, right? So mathematically that can exist. Then if mathematically that exists, why should we just go ahead and use that reverse SDE, which is giving us an approximate of the reverse trajectory, right? Why shouldn't we do it by our own, right? So maybe we can try to learn. I mean, we'll look at this. This is a very good trajectory forward, right? It's getting data, it makes noise, right? But for moving backward, for reverse move, maybe we can just learn it, right? So that was the idea. Maybe we can directly learn it, meaning that we say, okay, this is the forward trajectory. Every single time, the new x is going to be the previous x times some square root of alpha plus some noise with the remaining power. And when we just move like this forward, now we just come up with one solution, one approach that learns how it can move backward on this trajectory. So you got the idea? What is the idea now? So the whole diffusion thing we studied up to this point inspired us for this, which to my understanding is really necessary that we see why we want to do this. But right now, we're just having one statistical problem. So we don't have physics anymore involved here. Everybody's cool? OK. So now, the question that we have is that, OK, we have this Markov chain, forward diffusion. And now, what is the reverse diffusion? Meaning that if I start from the last sample, and I do just have one p, which is taking that one and sample from the previous one, can I make one p here, which is able to just every time generate a sample whose marginal distribution is exactly as the one I have on my forward trajectory, right? So for example, when I am at time t minus 1, at time t, I have distribution pt. Then when I pass it through this process, then I'm going to get xt minus 1, whose marginal distribution is pt minus 1, right? So this is the question, whether I can do this or not. Okay? And the answer, how we can do it, well, this is machine learning, right? We can think of this P as a kind of model, and then we can try to train this model in a way that it does this for us, right? The only thing is that we need to find out the right objective, right? The right risk function to minimize, right? So the main idea is that I don't know what is this trajectory, this distribution, which is going to move backward. So instead of just trying to use reverse SDE or anything like this, I try to learn it directly from the data, right? Now, here I have put this t here for you, right? Because I want to indicate that this distribution depends on time, right? Every single time it could be different. From a computational point of view, this is going to describe you one neural network. This neural network at particular time t, oh my God, I don't know, again, typo here. This is t, not t minus 1. Sorry, just fix it. So yeah, I mean, this is, I guess, the worst chapter for me because it's full of t minus 1. I told you this. I had a good name before. I was the king of typo when I was a student. The people used to call me king of typo. So just drop this -1 here. So this network, you can think of a neural network is going to get xt and also t itself. So at the particular time t, it's going to get the time and the sample, and then you just sample from the new distribution, right? You're going to give you the next distribution of xt -1, right? Now you have lots of samples, right? You have a data. You can put it on a forward data sample. You can put it on a forward diffusion, so it's going to generate all of those samples. And then you can use those samples to somehow come up with a solution training this model, right? If you can do this, then you are again moving backward from noise to data. Okay? Everybody's cool? Question? No question? Cool. Okay, now let me just go over the forward trajectory first, and then if you want, we could have 5 minutes break. Okay? Now, first thing, let's look at this forward trajectory. So for the forward trajectory, we do know what is the forward distribution, right? We had it here already. What is the distribution of xt given xt -1? This is this guy. This is the mean, right? Because xt every time is this guy with some noise. So this is going to be the mean value because I do know xt -1. So this is the mean value. And the variance is exactly the variance of this guy. Given that epsilon t has variance 1, then the variance of this guy is 1 minus alpha t, right? So this is going to be the distribution of xt given xt -1, right? So every time you have this process, Gaussian process, takes xt -1, computes the mean value, and then sample from the next time distribution, right? That's it. Okay, that is the way that you can look at it, but now let's start writing down those equations, right? So the first x1, this guy, is computed by a square root of alpha 1 times x0 plus a square root of 1 minus alpha 1 times epsilon 1, okay? So once again, alpha 1 is very close to 1, right? Alpha 1, yes, is very close to 1, meaning that 1 minus alpha 1 is very close to 0, right? So you have your data, you add a tiny bit of noise, right? Okay, now what about the next guy? The next guy is square root of alpha 2 times x1 plus some noise, right? So what you are doing, you get the noisy version, you again reduce its power, you add a bit of noise, right? And you go forward. But one thing that is obvious here is that I can take x1 here from the previous equation and replace it here, right? So let's write it down together. If I just write it down together, then alpha 1 going to come here, so it's going to be a square root of alpha 1, alpha 2 times x0 plus a bunch of terms which are all including noise, right? Given that epsilon 1 and epsilon 2, both of them are independent Gaussian processes, when they add up, they're going to be one Gaussian process again, with the mean being sum of the means, which is 0, and the variance being sum of the variances, right? If you simply do that, you're going to end up seeing this, which says that your x2 is this expression. You look at this, a square root of alpha 1, alpha 2, a square root of 1 minus alpha 1, alpha 2, right? So it's again the same process as the first one. Instead of alpha 1, now you have alpha 1, alpha 2, right? You see it? So it's true that you got x2 through x1, but in fact, x2 itself could be written directly in terms of data sample, right? Now, this is obvious. This is simply coming from the fact that everything is happening linear, and all those noise terms that you're adding are Gaussian, right? Okay, so what I can do, I can keep on going, and you can see that at one particular time t, you have always, in the forward direction, you have this term, which is the square root of the product of any alpha that you had from time 1 to time t, times your data sample, plus 1 minus exactly same term some Gaussian noise. Okay? So what you can say at every single time, you're eventually doing the same process, but this process is just gradually changing in the nature. As you go on in time, then that product of alpha values are going to shrink to 0, and that 1 minus product is going to exceed 1, and then you are getting from pure data to pure noise, right? But on the trajectory, what you are doing it step by step. You're adding the noises step by step. This is giving you the chance to just mimic the diffusion, right? Okay? Everybody's cool? So, from now on, I'm going to show this alpha bar term. So when I write alpha bar t here, I simply mean the product of all alphas from beginning of time to that point, right? And if we consider this one, then we could eventually say that at every single time, every single xt, we have the same process. So we have the same process as we had in every single jump in time, but instead of alpha, we have alpha bar, right? So now if you want to think about this direct link that you have from x0 to your particular time t, what you could say, okay, at time 1, I am just computing my x1 directly from x0, so both direct connection or just connection from the previous guy in the chain is going to be the same, right? But if I go at time 2, now I can think of x2 an immediate outcome of x1, which is x1 added with a tiny bit of noise, or I can look at it from x0 itself being noised, but this time, instead of being noised with a tiny bit of noise, a bit more noise, right? Because this alpha 2 bar is going to be alpha 1, alpha 2, and that one is smaller than alpha 2 itself, right? Because alpha 1 was smaller than 1, right? And if you keep on going like this in time, every time you could say, I get a tiny bit of noisy version from the previous time, but that guy, I can immediately write it down as a noisy version of my original data, right? Everybody's cool? I mean, that is quite simple, but this is going to help us a lot when we want to do variational inference. Okay, so this is going to be the case till you go for forever, and yeah, okay, you see, that was, okay. Anyways. Okay, and one thing that you should keep in mind is that as time goes on, this product, that alpha bar terms, are going to be 0. I mean, this is going to converge to 0, meaning that you are ending up with one Gaussian noise, which is 0 mean unit variance, right? No? Everybody clear? Okay, so what we can do in practice, we can think like if t is large enough, like 1,000, then eventually you are there, right? So that alpha bar t is eventually small enough that you can forget about it, right? Okay? Cool. So this is what is happening inside the forward process. So in the forward process, you can say always that even though you're walking on a forward trajectory, every single time you're computing a noisy version of your original data sample, right? And that noisy version, you can write down the explicit expression. So you can write down what is the distribution of your sample at time t given x0. You can write it down, even though you are not doing it in practice like this, right? You are adding it step by step. But every single step, you are able to write down distribution of xt given x0. And this is simply, this term is the mean value. So this is the mean value because I have x0. And the variance is eventually this term, right? Everybody's cool? Okay, so I do know the forward diffusion, how it works. I do know how I update every time. And I do know how I can write down the distribution of every single sample in the forward trajectory given the very beginning data sample, right? I do have these, right? Now the thing that I want to do, I want to find out a way to just build the reverse trajectory, the reverse Markov process, okay?